We've got here a gravity question. So the International Space Station is currently being constructed. It's incomplete at the moment, and the current mass is this. And they're giving us the orbit from the centre of the Earth. Here's some information: the mass of the ISS, the mass of the Earth, the radius of the Earth, the radius of the International Space Station, the gravitational constant. What's the weight of the ISS in its orbit? A silly mistake would be straight going equals mg equals 3.04 by 10 to the 5 times 10, because that's what gravity is. Not correct. Okay, because it is this g that we're used to being 10 is only at Earth's surface. When you get further out from Earth's surface, and this is here's the surface here, this size radius, and we're a little bit further out, gravity gets smaller. Okay, to work out what gravity is, it's g equals mass gravitational constant over r squared, and this is the mass of the thing you're circling. So here's the Earth here, here's Australia, here's New Zealand, and the International Space Station is going around like that, with the radius of the Earth, and we've got the radius of the ISS. The mass here we're going to use is the mass of the thing in the middle, so it's the mass of the Earth. And now that we've got g, we can just say it equals mass times little g. So this g, or the gravitational acceleration, is this. We sub it into this equation, we get mass, and this is the International Space Station, times mass of the Earth, times gravitational constant over r squared, which is ISS 3.04 by 10 to the 5 by mass of the Earth is 5.98 by 10 to the 24, gravitational constant 6.67 by 10 to the minus 11. The radius, what radius do we use? Do we use the radius of the Earth or the radius of the orbit? We have to use the radius of the orbit, this guy here. 6.72 by 10 to the 6. When you do that on your calculator, you get 2.69 by 10 to the 6 newtons. These gravity and satellite questions, people always make mistakes on their calculator, and I've just realised I've made one then. This is r squared, and on the bottom this is squared. That's still the right answer. I'd already done the calculation before I made the video, but you have to make sure you get everything right, like I've just mistaken here. So the r, this thing here, squared. Alright, what's the period of the orbit around Earth? Right, two of the equations you'll have on your cheat sheet, one of them looks like this. T equals the square root of 4 pi squared r cubed over gm. This is just about putting the right things in and getting the calculation right, like I nearly got wrong before. 4 pi squared. R, again we use the radius of the orbit, which is 6.72 by 10 to the 6. And it's r cubed. 6.67 by 10 to the minus 11, that's what g is. And then what do I use for m? What mass do I use? Again, you have to use the mass of the thing in the middle, the thing that's being orbited. So this does the orbiting around the Earth, so this is the mass we use, and the mass is 5.98 by 10 to the 24. And you come out with an answer of something like 5,480 seconds. When the ISS is completed in 2011, its mass will have increased to 3.7 by 10 to the 5. So at the moment, what is it? It's 3.04. It's going from 3.04 by 10 to the 5. And it's getting bigger to 370. And will this change the time period? Time of the orbit around the Earth. Will it be greater, the same, or less? Well, the formula is T equals the same one we used before, 4 pi squared r cubed over gm, and this is the mass of the Earth. It doesn't matter what the mass of the International Space Station is. Once it's up there and they've got to go at the right speed, its time period doesn't depend on its mass, only on the mass of the Earth and the radius it is away from that Earth. So it'll be the same.